Yeah, hello everybody, and welcome to this first webinar in a series of webinars on reinforcement learning in finance. So you might be aware of the fact that we recently started this community effort called QUANTS at Dev, which is targeted primarily towards quant developers. Whatever this might entail in practice, right? The quant developer can be found in different functions, departments, companies around the globe. So primarily, obviously, in the financial domain, this is where these terms are used intensively. But even if you are interested in the field only, I think you can also learn a lot on our Discord server. More on that later on, as well as during the webinars, the exchanges, and all the other activities that we plan for this year and the coming ones. I'm Yves, I'm a founder and CEO of the R Machine, as well as the Python Quants, and I'm also the initiator of the Quants at Dev group. Yeah, let me dive already into our topic of today. It is based primarily on code that you find in my book, Artificial Intelligence in Finance. And the topic itself was mainly chosen due to the fact that in the Discord group, there was kind of like an intensive discussion about reinforcement learning, the benefits, the drawbacks, the problems of applying it to finance. So I'm not promising the final solution to all the questions or problems that you might face, that you might have in practice, but I think we can cover the topic and then you can decide for yourselves, because I always provide like full code so that you can use the code and replicate the things that I do for yourself, or maybe adjust it, improve it. Of course, I would love to learn about your improvements and about your experiences. But again, basically the code is in particular at the beginning from AI and finance. I'm planning to show a bit more than what was possible to include in AI and finance. And also I've come up with some new stuff afterwards. So I've shown here or put in here also my other book, Python for Algo Trading, because in the group and what I do, the primary goal of using reinforcement learning and Q learning in particular applied to finance is usually trading, right? That you have something like a trading bot, an agent in the end, that you can let loose, and that is first trained and then is active on its own in the markets, right? So this is, I think, what every finance practitioner, student, academic is dreaming of, to come up with such a bot. So how far we come, we'll see. So here are now the links I've shared in the chat already, the link to the slides. So there are basically three things at this stage. There is a GitHub repo, which I've just created last minute. The repo contains the resources as they are currently stand, as I'm planning to use them. And as we go, I will add to the repo, I will update that, maybe you fork it so that you have the latest versions. Then you see in the middle here, the Discord server might be a little bit involved to type these characters, but if you have access to the slide deck, you can and of course just click on the link. You can also follow on Twitter. This is also something that we just started recently. There's not that much yet, but I'm planning to do quite a bit more. I said it before, we have a chat channel in Discord, and I would ask you to post your questions and comments in that chat channel, because this then remains in your own on the Discord server, and it documents a little bit the discussion, so that we can later on follow up maybe on different questions that might have been answered, might not have been answered, stay open, or maybe we can also document ideas there of what to do next in this context. So Discord server for today, please use the chat channel there. So reinforcement learning success stories. So I'm pretty sure everybody is aware of the major success stories, but just as a background for those who might be new in this field, there is what many people call the Bible of Reinforcement Learning by Sutton Bartle. This book here, Reinforcement Learning Introduction, it's, I think, a fantastic read. You find there many background information pieces with regard to reinforcement learning, how it developed over time, what the different approaches are, but in particular, what is of interest for us, therefore I've put it here last, it's Q learning and deep Q learning in particular. So I can only recommend this book. You find also electronic versions, free electronic versions of this book on the web. If you are more interested in like kind of the success stories on a high level, this is kind of like an easy read, maybe before you go to bed, before you fall asleep. I have listened to it also as an audiobook. It's pretty interesting to learn how the single success story started and what problems they faced, the teams, when they tackled different problems like self-driving cars in the beginning, recommender engines, playing Atari games, and all these stories up to or down to the playing the game of Go, which has even been documented in a Netflix documentary, which is also available on YouTube. So playing Atari games, I used to play these games like hell when I was young, so this was fantastic that we in our living rooms could get started playing these games long before the powerful machines that we today have available. When we speak of deep Q learning, right, implement maybe with TensorFlow or whatnot. Here is the paper. Again, I don't want to go into the details here. This is more like a reference for you. If you're interested, you can look it up. So for me, this was kind of like the relationship, even more so than I would say Go. I never played Go in my life, although I find this exciting. I played chess quite a bit, not well. I was more fascinated by the computational side, actually. Always, so this is fantastic, but playing Atari games, this was for me like the kicker. So really, there is kind of like an agent who can play Atari games better than a human being. This was for me when I was convinced there must be something to it. So Go and AlphaGo, right? For me, this was one of the first books that I read on superintelligence or artificial general intelligence. And I just want to emphasize here, in 2014, one of the leading researchers in the field, Nick Bostrom, predicted that it might take another 10 years, right, a decade, until the game of Go can be cracked by AI because it is so inherently complex. Yeah, it took like 1 year longer until the European champion was beaten, and in January 2016, the world champion was beaten. So we see here tremendous progress in terms of like hardware usage, like by Google here with TPUs instead of GPUs. Also the improvement of the algorithms and the self reinforcement learning during the training cycle. So fantastic stories. You should read it if you haven't done so. With chess, this was cracked before. Chess is not as complex overall as Go. And with a 10 million supercomputer named Deep Blue, IBM was able to beat Kasparov already at the end of the 1997s. But this has had hardly anything to do with AI. It was rather a brute force hardware game. And when you then have a look at AlphaZero, which is able to play against itself, and this is already a bit older, for 9 hours, and is better than any human being on earth in playing chess, and better than any machine that has ever been built or devised, like all these chess engines that have been growing over decades, basically, it is really fantastic. So there's no wonder that everybody, not only people in finance, are eager to try at least to apply reinforcement learning, Q learning, and some agent methods out of the field to other domains. Like, of course, in finance, we all know if you have a breakthrough there, this can mean immediately great riches that you can make in the market. So I'm thinking in terms of training. So coming already to the basic notions, of course, I have prepared code, but I think it's good to have some basic idea of what is going on there. And this is a framework which we will use, or the basic notions are things that we will encounter over and over again during my webinar series. And let's get started. First, we have an environment. That's the major thing with which any type of agent, whatever the algorithm is in the end, interacts, right? There's a problem at hand. So this can be a computer game, we have seen Atari, or it can be a financial market. Then we have a state of a computer game. This can be represented by pixels on the screen, or it can be represented by additional features, additional data points. Right, so that's the thing. In financial markets, we might have, I don't know, a collection of data points which say, well, this is the current interest rate, this is the current level of the S&P 500, whatever it might be that describes the state of the environment can be used in this context. We are going to keep it mostly pretty simple in this context. Then we have the agent. Well, it's not a person, it's more like an agent. Agent Smith in the matrix it's a computer program, right? A computer program, an algorithm, which is nevertheless able to act on its own, to interact with the environment, right? It learns from these interactions, updates the policy, and then hopefully improves playing the game, trading in the markets over time. Speaking of the agent, usually, at least in our cases, most of the cases, we have a limited set of actions. Let's say move the pedal to the left, move the pedal to the right, or in the markets go long or go short, or reduce the position or increase the position, right? Or exchange one asset for another might be another action. So we keep it simple here. Then we have a step. What is a step? Yeah, we move the environment forward step by step, right? So we have a state, we have a next state, and what happens in between is usually called a step. The beauty here when we work with software environments and not the real world via APIs is that we can basically decide on the speed. So it's not like, you know, that we need to be as slow as in the real world, or maybe as fast as something is in the real world. We can be slower or faster, right? So the step simply says we have a state and we move from one state to the other, right? And usually this only works forward, right? Like in real life, time is ticking, right? We cannot say, oh, well, this was a mistake, let's go back. This is only possible that we say, well, we do a replay or whatever, and then we learn from our mistakes. Then we have a reward, like in real life. If you do something good, at least when you're young, that's cool, right? You get a reward. Or when you do something not as good or wrong, you might get a penalty. So the same holds true here. Reward plays a major role in the updating of the optimal policy. And then we have a target. For a computer game, usually it's, I really recall this well. When I was young, we were playing like card games in some pubs back then. Young people could go alone to pubs, and we tried to crack the high score. The high score, this might be a target in a computer game. For financial trading, this might be the trading profit, right? P&L. Whatever, or a average return, or whatever you have as a financial benchmark yardstick that you consider appropriate. Of course, reward and target must somehow be related or closely related. Otherwise, it wouldn't really work in this context. Then we have the policy. Strictly speaking, the policy is the mind of the agent that simply says, when I see a state, I have a number of actions, and the policy says, given that state, given the possible actions, I choose action A, B, C, depending on how many actions there are available. So this can be move right, move left, or trading bot could say this is I go long or I go short. An episode is a whole game. Right? Back in the days when I was playing card games, I needed one Deutschmark to play one game. When my 3 lives were gone, the episode was over. So it's like a whole sequence of steps, actually. Before we get to Q learning, and in that sense, one of the most popular and most successful algorithms in reinforcement learning, let's dive into the code and let's have a look at OpenAI Gym. Because when you recall, my title was From Playing Games to Trading in the Markets. And now that I speak of code, right, I have the code here. I will basically execute this locally. You see there is the book where most of the code is from. There have been updates and adjustments, right? But the original things are coming from the book. Here's also reference Q learning. So we come to that a little bit later. I want to get started here with Gym. And having said that, there is the repository. So I will execute this locally. You see there's some stuff that is basically not needed here. So I can also delete that because when there is no visualization, we don't need this. I will execute it locally, but you have access to the GitHub repo, right? So here is the gist, not the gist, is the README. So I can also, again, for reference, share it in the chat. Git repo. So I put this in the Discord chat, right? And even if you don't want to install all the stuff that is required, basically it's not that much, at least in the beginning, right? You can use Colab. I recently got somehow a fan of Colab, basically out of being ignorant, unaware of all the nice features that Colab has. So if you go to, I have already executed something here, so I'm going to close this and use the link. Use the link that I provide here. It's a free tie-up. I don't have currently any subscription, right? But here, the link that I share, I can also share that one. In the chat. And when you open this link, you see this interactive prompt, and you need to just type in my username on GitHub, Hilfish, and then it now searches all the repos that are in my account. There are quite a few. So the first one, simply in alphabetical order, is AIIF. This is the code from the book, AI in Finance. There you'll find also, if you're interested, there you'll find also like how that works. And here, chapter 9, AB. It's a longer chapter on reinforcement learning. You find also the Jupyter notebooks there. But I want, of course, you see, I have quite a few. Where do we have it? It's RL Finance. Such a long list. And in RL Finance, in this current repo, there are just two at this stage, two Jupyter notebooks. And when I click on the first one, Colab opens it from the GitHub repo, and then you should be able to execute that as well. So that's kind of like pretty small. Usually you get prompted with the warning, this notebook was not authored by Google. I say run anyway, right? And it might take a little bit until single things are executed. I don't want to execute like everything in here. So then you can go step by step, and you see I now execute here the green check marks show that the cell has been executed. You also see the outputs here. So actually pretty convenient from the repo. You can wire Colab with the link that I've provided, open immediately such a notebook, and I checked the two of them that I'm going to use today. They should work out of the box. If you change things, make sure that you put them in Google Drive or whatever, whatever they offer as an option. Otherwise, you would lose on Colab your changes. So we have learned about the basics, the basic notions, and I now want to illustrate the basic notions here based on the so famous card pool environment. Let me see if I find a V1, let me check. I work with V0, V1 shouldn't make a big difference, so I'm looking up it here. And here you see it, this is what I was looking for. I have also a couple of notebooks used in the past where I had this visualization included in the notebook, but yeah, Jupyter Notebook is not really the best environment to do some visualizations like these. And you see, card pool is very simple. You have the card with a position, and you have the card speed, and you have then the pole on top of that. And the goal of the game, probably you've seen this, you've heard of it, maybe you've worked with it, is to balance the pole so that it doesn't fall over. Right? I think 15 degrees or whatnot is the limit when it falls over, and you lose this game. If you are able to survive 200 steps going forward one by one, then this is considered to be a success. It's not infinite. 200, they say, is success. You have quote unquote cracked the game, and there is another rule. Over 100 consecutive games, the agent shall have an average of 195 points, which means 195 steps on average survived, at least, in order to be considered a successful agent. There's one game, and then there's the additional one. So that's the Carpool OpenAI gym environment. How does this look like, right? When we would be playing a game as human beings, probably would have like a joystick or whatever and try to balance it, but this is not how reinforcement learning works. Let's see how it works on the API level. So I import gym, the environment, then the creation, the instantiation of an object, of such an object. I set a seed so that it's reproducible, right? And basically 2 seeds for the action space and the environment itself. And then I can, for example, inspect for the observation space. And we see the observation space has just 4 elements, right? I can observe potential values. I can also check here the low values, the lowest values, and you see this can be minus infinity in 2 cases, and here low value is minus 4.8 for the environment allowed and minus 0.41. I can also check for the high values. I'm just showing this, that this is all available here. For the implementations afterwards, this doesn't play a role for us, but in some circumstances, or depending on the algorithm that you use, this might be important to know. So how can we now work and interact with the environment and step the environment forward? So the first thing that we usually do is we reset the environment, right? Then we have a state, and this is with some randomness. I have here set a seed, right? So that when I go through the sequence of code, this should always be the same, but when I repeat this without setting the seed again, I get another initial state because the initial state has already some randomness. So it's not completely random. So we get something where the pole is upright. How this is done, we see a little bit later, or what this all represents. We see a little bit later. But we need to recognize here, it starts usually from a different initial state. So the initial state changes all the time in those cases where we do not fix the seed. The action space is just 2. We have 2 options, 2 actions that we can take, right? And we can randomly sample from the action space. So this is to get started with. You know, we don't have any agent yet who has any type of intelligence or insight into this problem here. We might have the need for random sampling, where we say, well, let's play this game randomly, more like rolling the dice in this context, right? We sample and see, by chance I get here 1, 0. I can repeat this, of course, a bunch of times, and I get zeros and ones. Let's now pick one arbitrarily, meaning randomly, 1, right? And what I do now is I step, and maybe this is not even here so pronounced, I step the environment from the initial state to the next state by taking action A. This is chosen randomly, no intelligence whatsoever, and I get back 4 different objects. State, we have 4 parameters. 1 is the reward, so I get +1, +1, +1. It's just like here, it represents success, right? +1, and done simply indicates whether I'm still in the game. So whenever we see there true, this means we have reached the very end, 200, or we have failed on the way. So false at this stage is pretty good because we are not yet done with it. So what are these numbers now about? This is a pretty simple thing. I said before that maybe we have a game and the state of the game is represented by pixels on the screen, right? But here it is different. So we have a physical simplification of it. We have the card position, the card velocity. We have the angle of the pole plus the angular velocity of the pole. So it's not about pixels here in this context, right? It's just about 4 physical parameters: position of the card, velocity of the card, the angle of the pole, and the angular velocity. So how fast this is dropping to the left or to the right. Right. In an ideal world, maybe somebody who has trained this for, I don't know, 15 years to perform in a circus, right? They have it completely straight up and only minuscule movements. But here you see this is really hectic. So what they show here is pretty hectic. And yeah, going left, right, the angle changes, angular velocity changes. And this is what these 4 numbers are about: precision. And overall, we don't really care in such a context what does 0.0378 stands for. Slightly right to the middle, I would say, right? But in the end, the agent doesn't have any clue. This is what we always need to internalize and remember. Doesn't have a clue what these 4 numbers are about. So the agent of our program takes 4 numbers as input, whatever they are, and then takes actions and see how the state changes after taking the action. This is recorded, and the agent then updates the policy given the reward that it receives, or no reward maybe, or sometimes a penalty. It's not like that the AI agent, the RL agent, needs any kind of visual representation, not even an explanation for what these are, right? The agent won't need any physical model, maybe, to write down some differential equations in order to predict what's happening when action A or B is taken. This works differently, and this is one of the beauty things. So let's simply do a quick run. A quick run in the sense of we only sample here, so randomly sample some actions. And you see in this particular run, after step 14, we fail because there must be some true here returned for done, so we are finished. But we are not successful in this context because, again, 200 steps is considered successful, right? So we failed here. This is what it says. Sometimes randomness is a bit better. So instead of 14, 27, and we can repeat this exercise a couple of times. So it's not that we fail immediately when we only go with random stuff, but usually it's kind of early and we can conclude it's far away from 200. So in order to solve the problem, we don't really need, for this particular environment and problem, we don't really need Q-learning, deep Q-learning, or whatever. There are other algorithms, and this is one that I first saw on this web page. And the idea is to reduce dimensionality, and that's the reason why I like to use and show this example, because this is something that is, I think, inherent in many machine learning, deep learning, and here we also see it later on in the reinforcement learning environment. We have something as complex as a physical problem. Here, it's a card, it's a pole on the card, we have the speed of the card, we have the pole angle, etc. Right? We see it visually represented, but this whole thing here is just boiled down to 4 physical parameters. This is already dimensionality reductions. If you would like to have all the pixels here of this game, this would of course give us more features that we would need to work with. But I want to go now one step further and further reduce dimensionality. I fix now the seed for NP, for NumPy, and I come up with some random weights. Why weights? Yeah, because the idea here is based on taking a product between 2 vectors. So how does it work? We have a now new initial state, which is fixed by the seeds. I haven't fixed the seed of the environment, so this doesn't fix it here. But when you go from the first cell to the last, then you will always get the same results. and I take the dot product between the state and the weights. And this gives me now a single number. So physical world, pictures, pixels, 4 physical parameters, dot product, now a single parameter only. So this is a further reduction of dimensionality. And the action rule now is conditioned on this single value that we have here, right? And how does it look? The idea is that we take action 0, move the whole thing to the left, or push it to the left, right? Card, right? We have the idea of pushing it. If S is negative, otherwise A equals 1, we push it in the other direction. By we, I mean here, of course, the agent, right? We are not interacting. We are not doing something manually. We want to have the software solving all the problems here. So in that sense, for the number that we see here, right, it's positive. Ergo, we get here a 1. I might try to come up with something else. Now we see the S value for the single state. S for state, it's just one number. We now get a 0. So the question is, does it work or not? Let's give it a try. I have now a function, a Python function, which takes the environment as an input and the weights. And with the weights, we now implement the whole episode here, right? And have what I've done here just once repeated as long as we are not done, right? When we get back done, then it's over, right? And we can now use the weights, and we get to 61, 95, 86, 126. So this is all these numbers. It's a little bit of luck here, by chance, are now larger than what you have seen before, where I was just randomly sampling the whole thing. But we now want to improve the whole story by saying, well, we have chosen the weights completely randomly, out of the blue, right? Who says that these are good weights? We could have gotten completely different weights. Maybe they would have been better or much worse. Who knows? So therefore, now by simple learning, where I fix the seeds now, and I want to do a maximum of 1,000 episodes. Usually it's in the low 2 digits. Set the seeds. What I want to do, I want to iterate as long as I have here not a successful set of weights discovered. And this is more like Monte Carlo simulation. So we repeat. We draw random weights and we apply the approach from before. And when we are getting to 200, then we say it's a success. When we are better than the previous result, we at least update and store the weights. So simple learning, but it's brute force. There's no intelligence, no representation. It's random, and we simply check what is good in our case. And you see here it's already after 13 episodes, 13 games, that we get these weights. So maybe let's here I set the seeds. Maybe I repeat the exercise. Here it's already after 9. So you see this is going pretty fast. 9, already after 6, after 7, sorry. So it doesn't take that long, and that's a little bit surprising, right? Here it's now 20, right? That we get weights that obviously with our rule, the algorithm, give us, a good chance of being successful with the game. So speaking of that, let's do the litmus test here, 100 runs, and then we calculate the average. I said above 195 is considered to be a successful agent. Here you see that's not a good one, right? I mean, it's good, but it's not considered successful because the average, as we will see, is well below 195. I think I have with the seed, value, I get something that is perfect. But you can play around. You see already here the first 10 are 200, 200, 200, right? And I get here a perfect result with these weights. So there's no guarantee that the weights that I've found here, even if they have shown once completely successful episode, will be always successful, right? Recall we have some randomness in the initial state, and that's now reflected, or has been reflected before. Here it's now a perfect agent. You can also go, I don't know, to 1,000 if you don't trust that it's still 200. Yeah, so we have the environment, we have the idea, the concept of dimensionality reduction. We have now used Putho's Monte Carlo simulation to come up with weights in combination with a decision rule, with an action rule, right? And we see this is already good enough to solve the problem here. So in other words, I don't need necessarily here yeah, a deep Q learning agent, whatnot, right, in order to solve this. Yeah, there's a question with regard to a trading related example. We come to trading, but we need to have the basics first. So finance and trading bots we will cover in the series a little bit later. Without the basics, it's pretty difficult to see how we best apply reinforcement learning and Q learning to a finance environment. So later on, just a little bit of an outlook, we will develop finance environments that behave more or less in the way like the OpenAI gym environments, where we can use the Q learning agents and let the Q learning agents interact with the finance environment. But at this stage, OpenAI Gym doesn't simply have a financial market environment. I don't know, US stock market or whatnot. This is not available. But I will share code which does exactly the trick with regard to trading, going long and short, etc. Right? So for these more involved problems and also for other OpenAI Gym environments, we need a bit more than just some random weights drawing, right? And yeah, a simple decision rule, we need probably something that is called Q learning. And when we talk about trading in financial markets and speaking of a reinforcement learning agent, usually what is meant here is Q learning, and in particular deep Q learning. In this context, we will work with a reward function. R that assigns to each state action pair a numerical reward. So we have seen this already. I have a state, the agent takes an action based on a policy, based randomly, and the reward is received. In the simple case of card pool, it can only be a 1. So I get, if I'm successful, I get one, another one. But this is not necessarily in other cases as well. Then we have the action policy, which is similar, but a little bit more involved, also looking into the future. A policy Q assigns to each state and allowed action, same, we start with the same starting points, a numerical value. So how is the numerical value composed? It is composed of the immediate reward, here we go, immediate reward, plus the discounted delayed reward. And that's kind of like the major thing in Q learning. It's not only what I get currently, but also what I get later on. This is, I mean, everybody knows this. When you play chess, for example, it's not kind of like that you just try to optimize for your next move. You think further forward, next move and the move there afterwards, and the reactions of your opponent, and grandmasters are able, I don't know, to simulate in their head like 7, 8, 9 moves, depending on how many pieces are on the board, right? So this is what we need to take into account. Not only our current move, but also what happens after. Also in real life, right? Do I eat the Snickers or not? Eating the Snickers gives me an immediate reward, but tomorrow when I go on the scale, I will have, I don't know, 250 grams on top of my previous weight. And here is the formula, which is important. We have the reward function plus gamma is a discount, the discount of the next state's optimal or reward based on the optimal action. So we maximize looking forward given our policy. So this, you see, this is related here, somewhat recursive, right? So we have immediate reward plus discounted delayed reward. We see it in action later on. Then we have a representation, the policy Q. For very simple case, think tic-tac-toe can be represented in a table. You have all the possible state action pairs, and then you write simply down what is to do in this case, right? But think of, I don't know, Atari card games. That's not possible, right? We cannot write down everything, so we need some representation for Q. And some approximation. And this is now where neural networks and where the deep Q learning comes from, that we have approximation capabilities of neural networks that are fantastic, universal approximation theorems, and we use the deep neural networks to represent, to approximate the optimal policy. This is now where we don't forget about deep learning. To the contrary, deep learning, deep neural networks are an essential feature of the environment. So here just a link to a paper and a statement with regard to a universal approximation. Then we have two types of actions. The one is a random one. We have seen this already. This is for exploration. So we need to interact fast, randomly with the environment to get feedback. And the more we have learned, the more feedback we have gotten, maybe the more we rely on the, at this point, current optimal policy and exploit this policy. So exploration simply means random action. Exploitation means an action given the optimal policy. Replay is used to retrain, to update the neural network. So we collect our experiences over time, and we use sampled experiences to train, to retrain, to update the neural network. Gamma, I said it already, is the discount factor. Epsilon is the ratio with which the algorithm relies on exploration as compared to exploitation, or to all the actions taken, right? Epsilon decay, this is another parameter that we can choose. This means that probably we begin with epsilon 100%, because in the beginning the neural network doesn't know anything with regards to the problem at hand. So we explore, and over time, when we have learned something, epsilon decay decreases the exploration and increases the exploitation. So we can, with epsilon decay, we can make this faster or slower, right? That is a pretty long-winded question, or a couple of questions, I think, at this point, with regard to trading bots, where we are with the basics. It's not that simple to say, and some people even say, well, reinforcement learning for trading doesn't really work. It might work for position sizing, it works maybe for hedging related trades, etc. Maybe we keep the discussion with regard to what works not, for a little bit later. And as usual, people who have maybe something that is successful in production, they probably won't tell you anything in this regard. Even machine learning in general, and then deep learning, and then reinforcement learning as a further subcategory, are, with regard to trading execution, still a minor part with what's going on in the markets. You hear like stocks are traded algorithmically to 80–90%, depending on the market that you look. Yes, but these are in general not AI-related, machine learning-related algorithms in this context, right? So this is what we need to be aware of. This is still all pretty nascent. Yeah, but sticking to the basics at this point, we will have enough time to discuss the pros and cons later on. Let's see how a simple Q learning agent might look. So there is a bunch of imports there. You know about the card pool environment, and I'm going to use TensorFlow Keras. Here, this should also work with the link to Colab that I showed before. I mean, it's from Google. They have TensorFlow versions installed. Let me check. I have here, I don't know, a little bit of an older version, but the code now should work with, I don't know, up to 2.7 or whatnot. I'm not aware, given the recent versions. This is what I have here on my Mac M1. by default installed, and I guess the code that was changed previously should work with the newer versions as well. So importing TensorFlow Keras, the single elements that we need, then dropout. I don't think I use dropout here. No, it's a simple, so even this here might not be required, but it doesn't hurt. I set a number of seeds to make it as reproducible as possible. So Python random, NumPy random, TensorFlow random, the environment in general, the environment action space. So 5 seeds that I fix, and now we come to the Q learning. For the storage, saving of the experiences, for the replay, I use DECQ. This is basically a list object where you can specify how many elements are allowed, and it works like a queue, right? Once you have reached 2000 and you append something, the very first element in the previous state is dropped, right? So you have a maximum, you see here, maximum length of 2000 for the DECQ. So that we don't have the old experiences that have been included already in the neural network. We just work with newer, more recent experiences, reflecting that over time the agent will rely more on what is learned. So we simply forget. I mean, this is like when you start, I don't know, playing tennis or any other game. If you listen to this, and you probably won't recall your not so fantastic first matches, rather the ones when you are better and you want to learn and take it from there a little bit later on. So the DQL agent, let's have a look. It looks long, but given all the notions that we have discussed, it's, I think, with Python background, not too difficult to understand. So I'm not going into every single detail here. You can work with the code, you have access to the code, you should go through it, maybe you change parameters. Finish is just used here so that I say I finish early, maybe depending on what the problem is. Not every problem that we might face is like Cardpool, which simply ends at 200, right? It can be at, can also run infinitely or whatnot, right? Epsilon, exploration, we start with 100%. The lowest value should be 1%, and epsilon decay is 99.5%. Gamma here is set to 95. That's the discount factor. The batch size is used in the replay. I collect averages here for the success rate. So to see how it improves, not game by game, episode by episode, but for the last 25. DECQ, I explained it. I was executing the cell because it's so long. Drop down. And here this is just used for the building of the model, and here the model is split. This is a very simple deep neural network, nothing special. I have one layer, a second hidden layer, and here we are already at the output layer, right? So it's it can be considered deep because we have 2 layers. It's not simple or shallow, but it's not, you see, by default with 24 hidden units. That's a pretty small neural network. Then we have here the ACT method, right? We see whenever we draw a random number, which is, this is uniformly distributed between 0 and 1, whenever this value is below the current self epsilon, then we do exploration. Otherwise, we rely here on our optimal policy. Replay is to train, to retrain, to update the neural network, which represents Q, recall Q policy, hopefully optimal from a certain point on. And here we have the reward. The reward here is from my randomly sampled element in batch, and reward plus equals self gamma. This is now where the second expression in the optimal policy function comes to fruition, and then we update it and train the model here, basically experience by experience. So when you are used to more to deep learning models or standard regression models, classification models, you have, I don't know, 5,000 rows, data rows with 10 features and 5,000 labels, right? You do it in one step. Here, reinforcement learning is kind of a pretty sequential exercise, and this makes it computationally hard. There are, of course, mechanisms and techniques to parallelize stuff, but the base algorithm here you see is implemented sequentially. Therefore, it takes quite a bit longer as compared to something else where we have like even 1 million data points and train like a classifier on 1 million data points of features and labels in a single step or in a single learn training run, right? Now the learning, without going into every detail, I have a number of episodes that I play. I reset the environment, get a state, then I take the action. I collect next state, reward, done, info as before. There's a little bit of reshaping going on for appropriate shapes to be passed, and I append this to memory. Recall this is that queue, that's a queue. A maximum of 2,000 such list objects are collected there, right? And when we are done, we do a couple of calculations here in this context. So meaning we get the number of rewards, total number of rewards, then we calculate some average here over the last 25 episodes, and we store the maximum reward so that we see, do we have some improvement at this stage or not, and we print out. Right? If the average is above 195, this was the finish flag from before, and here's the finish flag, then we stop. Right? This is like the rule that I have discussed before and have shown with a simple dimensionality reduction approach there. Right? So 195 is considered successful. Finish is set to false here. Test is simply a helper method which allows me to test the optimal policy in the sense of that test completely relies on exploitation and there is no exploration going on. I mean, this makes sense, right? After you have trained, I don't know if you're playing soccer, football, for example, you go to the training, you do here and there, but once there is the day is Saturday for competition, there is no exploration anymore. You simply do the best you can, and this is what is simulated here. So let's say we would would go with a maximum of 500 episodes. I set the seeds again here. The DQL agent is instantiated with gamma 0.9 by default. I simply have changed here a couple of values. You can play around with different values. Discount factor 0.9, hidden units 20, finish true. I argumented, so whenever the average is above, at a certain point, is above 195, we finish early, and let's do it in straight. And we will see now, before this was all pretty fast, I didn't know, in the millisecond range. Now training will take time, right? 500 episodes, and you see it's going kind of fast, but still it takes a bit. You see total reward is jumping up and down. In between, we've had a maximum of 200 already, and the average goes up and down. Even it's not like that it's going linearly up or up overall, whether linear or not. So it's improving and it's getting worse. And maybe we check just to get a good feel for it. Agent epsilon, because the numbers are varying that much, right? We still have 8% at this stage with that many episodes. We still have epsilon of which means exploration, random sampling of 8%. Right? So how does it look with regard to the average number? So this is the trend. This is the moving average of the successes, right? This is like looking backwards 25 episodes already. Here it was above 125, it goes back down, up, down. You see overall the trend. I think this is a cubic regression, or what do I use? I use a cubic regression. Here overall it's getting better and better, right? You see here, the more training the better. This is like with AlphaZero, 9 hours of chess, probably ceteris paribus, when AlphaZero is training for 2 hours and then for 3 hours, we would expect the version with 3 hours of training to be better than 2, and once it is trained 8 or 9 hours, we want this to be much better than the version from 2 or 3 hours, right? So this is what we see here as well. Over time, we're getting better, but not perfect, right? It's not like that it goes like straight up here as the regression line would suggest. So the test now, let's see. This is still pretty jumping around here, and we get an average of 139. So even with a deep Q learning edge, it's not that simple to crack here the card pull problem. Although we have now used a much more sophisticated approach, which is much more flexible than the one that we had before, because it can apply to many other scenarios and environments, etc. For example, we could have something with 8 inputs, 8 features, instead of just 4 or whatever. That's pretty flexible in this regard, right? But the whole work that we've done, the many lines of code, don't bring us after 30 seconds more better results, right? We can of course always put in more effort. So I now go here with another run, and this might help improving, right? But still there is no guarantee, but we would expect it after a certain period of time that it's then quite a bit better. You see now the average is staying on a relatively high level. A little bit of luck is here involved as well. Let me see whether it works. I think we're just on time because it's the final thing that I wanted to show. Looking at the questions, there haven't been that many questions so far here with regard to the basics. Again, the discussion how this works in finance, etc. We should get back to something a bit later. Yeah, with regard to the notebooks, or with regard to notebooks, I've shared the repo. Sure. I don't know from when the question was with regard to notebooks sharing. Have a look at this here. Yeah, it started from scratch, and here it stopped kind of early. So let's see how this now works. And after some intensive retraining, right, we now got a deep Q learning agent, which is also perfect when it plays 100 games. But you saw this is like kind of evolved. We had like 30 seconds and 44 seconds. So overall, this took like a minute and 15 seconds, 75 seconds. Where we compared this with our simple approach here. This was all lightning fast, right? Pretty simple. Some dot product is of course easily calculated, and random numbers are also drawn at for us human beings at least. It feels like the speed of light, right? So this is pretty fast. But deep Q learning, now we have the basics, the notions, how such a deep Q learning agent looks like, and one of the next steps will be to apply this now to a yet to be designed, yet to be introduced finance environment, which shall behave like the OpenAI gym environment. So this will be one of my approaches that I said, well, we have the DQL agent now, deep Q learning agent. This agent with enough training was able to play card pull perfectly. Can we use the same agent to attack a trading problem? And I say yes, but we need an appropriate finance environment. The what do I want to say? This is a little bit in analogy to the AlphaGo story. It more or less had the major breakthroughs with AlphaGo, but later on they used the setup, the algorithms, etc., to crack chess as well. So when it was so good at playing Go, why not try it with chess? And here it's a little bit of the same idea that I want to follow, to say, well, this is now able to play card pull perfectly. Why don't we use it with another environment and try and see how the deep Q learning agent performs with a financial environment. This is in terms of the basics and the basic framework that I wanted to introduce based on card pull. Finance next. that I wanted to introduce today. You have access to the code. You can execute the code in Colab, for example, or of course you can download it, install the stuff if you haven't already with pip or conda, for example, and can try it yourself. So there will be more on the topic. Don't forget to come to our Discord server, where there are like almost 24/7 discussions are going on. The group, as it stands right now, has 400 plus members. Also, the Twitter account is worth following, because there, for example, you will find announcements for the events, not probably mine, maybe for others as well, and some more information. And I will also upload the recording of today's session to a YouTube channel that I recently created with same handles, QUANTS dev, and I will share the links then to the recording as well. In that sense, let's check. There seem to be no further questions. There is another question. Again, there's a question related to finance. I'm not suggesting here out of the blue features for price action. This is something that we can discuss then in the context. Otherwise, it's here a little bit without relationship. But let me say one thing in general: you usually are responsible to do your research and saying which features do I consider relevant. And basically, whatever you come up with, which is price related or whatever, for whatever you have data for, you can include in the exercise. So there's really no limit. When you say, well, I have something that I use with a standard deep learning classification algorithm, you are probably able to use it in a similar fashion, at least with a reinforcement learning agent there as well, right? All right, having said that, I wish you happy reinforcement learning. This time for playing games first, finance second. I hope I see you on the Discord server for the discussion, and I'm planning roughly to do such a webinar on a weekly basis, so more to come soon. I will update the repo, etc. Also happy to hear your feedback. In the meantime, take care. Bye-bye.